14 years ago, a signal that had been traveling since before most living scientists were born finally crossed a threshold no signal had crossed before. The instruments carried no drama in their readings, only a shift in particle density, a change in magnetic orientation, a quiet recalibration of everything scientists thought they knew about the edge of home. Voyager 1 had left the heliosphere, the vast bubble of charged particles the sun exhales in every direction, a bubble that had, until that moment, contained every measurement humanity had ever taken of the universe beyond itself. Beyond that boundary, the heliopause, lay a domain the sun's influence could no longer reach. Voyager's significance was not that it observed the boundary remotely, but that it physically carried instruments across it. Not a telescope pointed toward it, not a model describing it. A physical object, built by human hands, was now sitting inside interstellar space, and its instruments kept working. For the first time, humanity was not looking at the space between stars from a distance of light years. It was standing inside it. That single fact, arrival, not observation, is the thread that runs through everything else in this story. Every crisis this spacecraft has survived, every instrument it has sacrificed, every strange signal it has caught, traces back to the same stubborn premise, that presence teaches you things distance never can. To see how deep that premise runs, we have to go back much further than 2012, all the way to the beginning. Rewind the tape 3.5 decades. September 5th, 1977, Kennedy Space Center, Florida. A rocket carries a spacecraft that engineers do not expect to become historic. The mission plan is modest by any measure: a flyby of Jupiter, a flyby of Saturn, a handful of years of operation before the machine goes silent and the data stops. 4 years, maybe 5. That is the number written into the mission's expected lifetime. Nobody signs up to build a legend. They sign up to meet a deadline. And then the deadline is met, and the spacecraft simply does not stop. It didn't stop at Jupiter. It didn't stop at Saturn. And decades later, it still hasn't stopped, which is exactly why, 40 years after that launch, something showed up in its data that no one had written into any model at all. Now jump forward, past Jupiter, past Saturn, past the outer planets entirely, to a single year, 2017. Something arrives in the data that nobody had written into any model. Not a spike, not a burst, not the kind of transient blip that instruments are built to catch and move past. A narrow band emission, continuous, persistent. Voyager's plasma wave instrument is registering a signal that does not fade, a signal that keeps recurring, year after year, spread across a region of interstellar space so vast it stretches for more than 900 million miles. For scale, the distance between Earth and the Sun is roughly 93 million miles. The structure Voyager was tracing was more than 10 times that span, not a localized anomaly, but a feature woven into the fabric of the space between stars. Research later published in the peer-reviewed journal Nature Astronomy confirmed what the raw numbers already suggested. The plasma beyond the heliopause carries turbulence and structure across scales ranging from mere meters to millions of miles. Here is what makes that signal worth pausing on. The instrument recording it was never built to take a photograph of empty space. It was built to listen. Picture it this way: charged particles moving through a plasma generate oscillations, the same way air molecules pushed by a vibrating string generate what we call sound. You cannot see the air move when a violin plays, but your ear converts that invisible motion into music. Voyager's plasma wave instrument performs the same translation, except its ear is tuned to electric fields instead of air pressure. And what it hears is not music, but the physical pulse of a medium no human sense could otherwise detect. It has no eyes for interstellar space. It has something closer to hearing, and for nearly a decade now, it has been listening to a hum that theoretical models never predicted, because those models were built from equations, and direct sampling revealed variables that remote observations could not constrain. What Voyager proved is not simply that interstellar space is noisier than expected. It proved that the only way to know an environment you have never occupied is to send something into it that can feel what you cannot yet imagine. That is not a limitation of 1970s engineering. It is a permanent limitation of theory itself. And no future model, however elegant, will ever fully replace the raw, unglamorous act of measuring a place from within it. Hold on to that idea, because it resurfaces almost everywhere else in this story. In a crossing 5 years earlier that this same instrument helped confirm, and in a crisis 6 years later that would test just how far a 50-year-old machine could be trusted to keep listening at all. From here, let the timeline run forward, uninterrupted, to the present. March 1979, Voyager 1 sweeps past Jupiter, returning the first close-range images of the solar system's largest planet ever captured by any human instrument. November 1980, it swings past Saturn, using the planet's gravity as a slingshot, gaining velocity, and pressing on into territory no mission had been funded to reach. By the close of the 1980s, it has become the most distant object humanity has ever built, and its instruments are still drawing power, still relaying a signal too faint for any layperson to detect, but unmistakable to the antennas straining to catch it across the growing gulf. That same protective bubble Voyager eventually left behind, the heliosphere, is not merely a boundary marker on a diagram. It functions as a shield, dampening the intensity of high-energy cosmic particles that originate from distant stellar explosions elsewhere in the galaxy before they reach the inner solar system, including Earth. Voyager's readings from beyond that shield revealed an environment more turbulent, more structured, than the calm and empty region scientists had long assumed it to be. What that turbulence means for the long-term stability of the heliosphere itself is still an open question, one Voyager raised but could not answer alone. And now, 2026. The spacecraft is still moving, still transmitting. They built it to operate on about 4 watts of transmitter power, less than many modern Wi-Fi routers consume simply maintaining a connection inside a home. Despite the fact that Voyager was designed before the digital age that now surrounds us, a machine assembled before the internet existed, still returning measurements from a region of space no human being has ever set foot in. In the months ahead, it will cross another distance marker, another number no human-built object has ever reached. It was never engineered to last this long. It was never expected to travel this far. And yet, across nearly 50 years, a probe designed for a 4-year planetary tour has become something else entirely. Humanity's first standing witness among the stars, still sending its faint signal home across a darkness it was never supposed to survive long enough to describe. But still transmitting is not the same as transmitting without incident. 3 years before this present moment, that signal nearly broke for good. The year is 2023, and somewhere across a gulf of 15 billion miles, a machine built before the invention of the personal computer is dying quietly, not with an alarm, not with a final transmission of static and silence. The spacecraft had not fallen silent. Its transmitter was still reaching Earth, carrying a stream of information across the darkness. But somewhere inside that stream, the meaning had been lost. The signal survived. The message did not. For months, engineers at NASA's Jet Propulsion Laboratory watched as Voyager continued sending back transmissions that arrived normally from space, but failed when processed on Earth. The team could confirm that the spacecraft was active, yet the information it returned no longer matched the patterns they had spent decades learning to interpret. The spacecraft is alive. Its carrier signal still arrives, faint but present, but the content inside that signal has become noise. Eventually, the cause is traced to something almost absurdly small. The investigation eventually pointed to aging hardware within Voyager's flight data system. After decades exposed to the harsh radiation environment of deep space, a small electronic component had deteriorated and begun interfering with the software responsible for preparing scientific measurements for transmission. That chip corrupted the portion of the flight data system responsible for organizing scientific output. There is no dramatic failure event to point to. There is only entropy, patiently doing its work across 50 years. To understand exactly how dangerous that kind of failure is for a machine this far away, you need to understand something about the mechanics of talking to it at all, and that requires going back further still, to a decade before the crisis, when the delay itself was already the whole problem. To understand why this crisis was so dangerous, you have to go back not to the beginning of the mission, but to 2005, when Voyager 1 was still years away from its next great milestone. By then, the spacecraft had already spent decades pushing outward through the solar system, and every exchange between it and Earth had become an exercise in radical patience. The distance between Voyager and Earth transformed every repair attempt into a slow experiment. Commands sent from mission control required almost an entire day before reaching the spacecraft, and engineers had to wait just as long before seeing the result. A single round of testing unfolded across a delay measured in days, leaving no room for quick corrections or real-time intervention. A single question and answer cycle, nearly 44 hours, consumed entirely by distance. Engineers of that era were not controlling a spacecraft in any real-time sense. They were making decisions 2 days in advance, sending instructions into a void, and waiting to learn long after the fact whether their assumptions about a machine 15 billion miles away had been correct. This is the operating reality that made the 2023 crisis so perilous. There would be no rapid diagnostics, no live troubleshooting. Any fix would have to survive an 88-hour round trip of guesswork before anyone knew if it worked at all. That same unforgiving delay is also, strangely, part of what makes an earlier discovery worth returning to. Because whatever Voyager found at the heliopause in 2012, it found alone, with no way to ask Earth for a second opinion in real time. Now the story moves further back still, to 2012, the same crossing we opened with, and arguably the moment Voyager 1 earned its place in the history of human exploration. Scientists had spent decades picturing that boundary as something soft and gradual, a slow fade, like a river losing itself in an ocean, solar particles thinning out as galactic particles quietly took their place. What Voyager 1 actually measured was nothing of the kind. Particles here moved at velocities approaching a significant fraction of the speed of light, colliding with enough energy to generate temperatures near 30,000 degrees Celsius. A region expected to be cold and nearly empty turned out to be seething with activity. And within that seething boundary, Voyager detected something even stranger. The magnetic field carried outward by the sun, and the magnetic field of interstellar space were not simply sitting side by side. They were interacting through a process called magnetic reconnection. Picture two vast, invisible networks of elastic threads, each stretched taut across its own domain, one woven by the sun's outflowing plasma, the other by the ambient magnetic field of the galaxy. Under the right conditions, threads from these two separate networks don't just brush past one another, they snap, reconnect to threads from the other network, and in that instant of rearrangement, release the energy that had been stored in their original configuration. That is magnetic reconnection, not a collision of objects, but a restructuring of invisible tension, translated into heat, motion, and particle acceleration. It is the same basic mechanism that powers solar flares, just enacted here, quietly, at the edge of the sun's domain, 15 billion miles from where it was first observed on the surface of our own star. What this told scientists was something the bubble model of the solar system had never anticipated. Our solar system is not sealed off from the galaxy. It has a living, energetic seam where it meets the wider cosmos, and the fact that a single spacecraft, using instruments designed in the 1970s, could detect a process operating at the scale of star systems is perhaps the clearest evidence we have that rigorous, patient observation can still outperform even our best theoretical models. 9 years and one broken data system separate that discovery from the moment engineers finally worked out how to save the mission that made it possible. Which brings us back to 2024, and the resolution of the crisis that opened this story. The engineers at JPL determined that the corrupted code could not be repaired where it sat. So they did something almost unthinkable for a machine of Voyager's age. They relocated it. The damaged section of software was broken into smaller pieces, and those pieces were moved into unused areas of the spacecraft's memory. Each one checked, rewritten, and reconnected. A kind of remote neurosurgery performed not with instruments but with mathematics and radio waves. Every step of it filtered through that same 44-hour communication delay first felt back in 2005. By mid-2024, Voyager 1 was transmitting clean, readable data once again, including new measurements of persistent, unexplained plasma oscillations in interstellar space, further evidence that the turbulent region beyond the heliopause is still not fully understood. All of it traces back to 1977, to a launch designed for a mission expected to last only a few years. Instead, the spacecraft has operated for nearly 5 decades, in an environment where a single command takes almost a full day to arrive, where a boundary once thought to be a simple line has revealed itself as an active, energetic frontier, and where one degraded ship nearly silenced humanity's most distant voice. It did not. And somewhere past the reach of any repair mission Earth could ever send, that voice is still speaking proof, each time, that the map we draw of the universe is never quite as simple as the universe itself. Proof, too, that the story of this spacecraft was never really finished in 2024. It was only catching its breath before the next milestone, one measured not in miles, but in something closer to time itself. At approximately 10:00 p.m. Pacific Standard Time on November 17, 2026, a number on a screen at NASA's Jet Propulsion Laboratory will cross a threshold that no engineering team has ever confronted before. Not a threshold of distance, a threshold of time. Voyager 1, the most remote object ever built by human hands, will arrive at exactly one light day from Earth, a gulf so vast that light itself, the fastest thing the universe permits, requires a full 24 hours to cross it. Send a greeting on Monday morning. It reaches the spacecraft on Tuesday. Whatever answer comes back, if it comes back, will not touch Earth until Wednesday. 2 days folded around a single exchange of words. Even now, before the threshold is crossed, the delay already sits above 22 hours. The difference between where Voyager 1 is today and where it will be in November is only a few final hours of drift, the last narrow margin before an entire day separates question from answer. This is not a milestone measured in kilometers. It is a milestone measured in patience. But rewind first, not to the beginning, to a quieter, harder moment that made this milestone possible at all, one that happened only months before this story reaches you. Earlier in 2026, inside a control room built for decisions no one wants to make, engineers at JPL switched off Voyager 1's low-energy charged particle experiment. The instrument had not failed. It was still functioning, still returning clean data from a region of space no human instrument had ever measured before. What failed was the power to keep it running. There was no astronaut who could be sent to replace a part, no shuttle that could close the distance, no second attempt if the wrong system were sacrificed, only a command crossing billions of kilometers of emptiness, asking hardware built almost 50 years earlier to do exactly as told, and nothing more. One can imagine the particular weight of that choice, not an emergency, not a malfunction, but a slow, deliberate act of triage performed by people who understood that switching off a working instrument means closing a scientific question that may never reopen, while every watt saved elsewhere is a watt spent buying the mission more years. There is no dramatic failure here, only arithmetic and the discipline to accept what the arithmetic demands, to understand why that arithmetic exists at all, why a working instrument had to be sacrificed for a few more years of life. You have to go back to the very beginning of the power budget that made this whole mission possible in the first place. Now go back further still, to 1977, before either of those later moments existed even as a possibility. Voyager 1 launched carrying instruments built for the outer planets, Jupiter, Saturn, the edge of what was then considered the known solar system. It also carried something that had nothing to do with particle physics or magnetic fields. A gold-coated copper disc, 55 human languages of greeting, the sound of rain, of ocean, of laughter, 90 minutes of music drawn from across human civilization, diagrams intended to explain the basic mathematics of a species that once looked outward, and a map that used the timing of distant pulsars to mark, for whatever might one day find it, exactly where Earth sits in the galaxy. Carl Sagan, who helped design it, called it a bottle cast into a cosmic ocean. In 1977, no one knew how far the bottle would travel, or for how long the sea would carry it before the last current released it. To understand why that journey now has a foreseeable horizon, it helps to understand what has been quietly keeping Voyager 1 alive for nearly 50 years. Inside the spacecraft sit 3 radioisotope thermoelectric generators, and inside those, plutonium-238, decaying at its own unhurried atomic pace. Picture not an engine burning fuel, but something closer to a small furnace with no flame, heat released simply because the atoms are changing, slowly, on their own schedule, and a thermoelectric material converting a fraction of that warmth directly into electricity. No moving parts, no combustion, no refueling possible across billions of kilometers of vacuum. At launch, this quiet furnace produced about 470 watts. Today it produces roughly 250, shedding about 4 watts every year, a decline as steady and indifferent as the decay that drives it. What this reveals is not a flaw in the design, quite the opposite. It reveals that the hardest problem in deep space exploration was never reaching the unknown. It was sustaining the capacity to keep listening once you had already arrived, for decades longer than anyone building the spacecraft had dared to promise. Scientific endurance, in this light, becomes its own kind of discovery, proof that a mission's greatest achievement can be simply refusing to end on schedule. Return, now, to the spacecraft itself. Alone in the dark, it has been crossing for 49 years. Of the 10 instrument packages it once carried, 7 have already gone silent. Not from failure, but from necessity. Each shut down a negotiation between one experiment and the survival of the whole. To the engineers who tended, Voyager 1 is not merely a collection of electronics drifting further from reach each year. It is decades of scientific history still transmitting from the edge of the solar system, still asking to be understood by people who, in many cases, were not yet born when it launched. Voyager 1 itself does not know any of this in any sense a human would recognize, but something in the image persists regardless. a machine built before most of the engineers now managing it were born, still answering commands that take nearly a full day to arrive, still returning a signal fainter than the light of a household bulb, across a distance that keeps growing by roughly 38,000 miles every hour. There is a kind of loneliness in that image that costs nothing to imagine and nothing to overstate. A single point of engineered light, receding. And so to the years ahead, where the story no longer needs another leap backward, only forward, in the direction Voyager 1 is already moving. No one at JPL can name the exact day, but the direction admits no ambiguity. One by one, the last measurements will stop. The final signal will cross that same widening light-time gap and arrive, and that will be the end of the conversation. It will not be the end of the journey. What a spacecraft does once no one on Earth is listening anymore is its own kind of story, and it's one worth telling properly. Once we've circled back to where all of this started, the plasma had been humming for years before anyone was certain what they were hearing. We already know the shape of that signal, the narrow, continuous hum first picked up in 2017. What's easy to miss is what it replaced. Before it, researchers had only caught interstellar plasma in fragments, the aftershocks of solar eruptions rippling outward until they struck the heliopause. Flashes, not a witness. To understand why that distinction matters, it helps to think of something far simpler than a spacecraft. Picture a stone dropped into a still lake. The ripples that spread outward are not noise. They carry information about the water's depth, its temperature, the disturbances moving through it. Plasma in interstellar space behaves in a comparable way. Charged particles colliding and interacting generate their own kind of ripple, plasma waves, that encode data about the density and temperature of the medium they pass through. What Voyager 1 detected may be thermally excited plasma oscillations, a phenomenon that fits neatly into existing models. Or it may be quasi-thermal noise, a different mechanism entirely, one that could force scientists to revise their understanding of what lies between the stars. This is the quiet radicalism of the discovery. If the signal turns out to be quasi-thermal noise rather than a thermally excited oscillation, the models built from decades of Earth-based and heliospheric observation will need a specific correction, one that no simulation could have supplied, because no instrument before Voyager 1 had sat inside the interstellar medium long enough to tell the two apart. That, more than the distance traveled or the years endured, is Voyager 1's deepest scientific contribution, proof that reaching a place in person can change the very questions we know to ask. Go back further. September 1977. At NASA's Jet Propulsion Laboratory, engineers were preparing a machine assembled from technology that predated the personal computer. Its mission brief called for 5 years of operation. Nothing in its design promised more than that. No one signing off on its trajectory could have imagined a signal from that same spacecraft still crossing the solar system's edge, still being decoded on Earth, nearly half a century later. Now return to the present. Somewhere at JPL today, teams responsible for Voyager 1 are making decisions no engineer in 1977 could have anticipated having to make. The spacecraft's power is finite and falling, and every choice carries a cost measured in silence. Shut down one instrument to keep another breathing a little longer, and some thread of data is lost forever, with no way to recover it. There is no repair mission possible across this distance. There is only the slow, deliberate rationing of a voice that cannot be renewed, a kind of stewardship closer to hospice than engineering, choosing not whether the spacecraft will fall quiet, but how it gets to speak in its final years. That decline has a clear direction, even without a fixed date. Each year, fewer instruments remain powered. Each year, the window onto interstellar space narrows a little further. Sometime in the early 2030s, the last active instrument aboard Voyager 1 will cross its minimum power threshold. One final signal will begin its long crossing back to Earth, arrive and be recorded. After that, there will be nothing more to receive. But that will not be the end of the journey. And this, finally, is where that ending actually lives. The spacecraft itself will not stop. Interstellar space offers Voyager 1 nothing to push against. No atmosphere, no meaningful friction, no gravity strong enough to call it home. It will keep moving at the same 38,000 miles per hour it has held since its last flyby past Saturn, carrying no instruments capable of measuring anything, and no capacity to say so. The communication delay that once measured hours, then a full day, will simply keep lengthening, unread by anyone, unanswered by anything, and still attached will be the golden record, a disk that currently runs on less power than a household light, and yet has carried humanity farther from home than any object in history. The golden record will continue outward long after Voyager falls silent, a map of where a small, curious species once stood, long after the spacecraft that carries it has gone quiet. Unable to send so much as a whisper back across the dark it helped measure, the record will still be moving, carrying without needing to say so, the fact that someone once wondered what lay beyond the horizon and built something that could go find out. What comes after is, for now, an open question with no funded answer. No mission currently exists to take up Voyager 1's role at the edge of the heliosphere. Even if one were approved and launched today, it would need at least 25 years simply to reach the boundary Voyager 1 crossed decades ago. When this signal finally goes quiet, the particular vantage point it has given humanity may not be recovered for a generation. For nearly 50 years, a machine built for a 5-year assignment has endured cold, radiation, and dwindling power to keep a conversation open across a distance that resists comprehension. Its instruments are aging, its voice is fading, but for now, it is still transmitting, and on Earth, 22 hours behind, we are still listening. You've been watching Beyond Astrora. Thank you for exploring the universe with us. Until next time, keep looking beyond the stars.